My name's Benjamin Jones. I'm an Associate Professor at the University of Nottingham, and this talk is entitled Dallying with DALYs, Why Acceptable Indoor Air Quality Should Consider Harm. I have lots of wonderful conversations with people about indoor air quality, and we generally tend to agree on two of the three words, but the third one is where discussion starts to happen. So we agree that we're interested in contaminants in the air rather than the invisible gaseous substances that surround the Earth, which comprise a mixture of nitrogen, oxygen and argon. But it's not those, it's the things that we don't ordinarily expect to be in the air. And then we agree that we are interested in the air in a building and that the building is affected by air immediately around it too. It's when we come to quality that the discussion gets a little bit more diverse. Now, quality is a measure of excellence, so it is a relative parameter. So, for example, we considered the horse to be an excellent mode of transport until the car was invented. So that concept of quality may change over time, and I think it does too with indoor air quality, and I'm going to discuss that as I go through the talk. So when we think of indoor air quality, it is relative to something, but are we considering the quality of indoor air relative to it being completely uncontaminated? This may not be an efficient approach because we may be expending resources on designing, manufacturing and running systems that are unnecessary if the contaminants in air are not themselves harmful. So how should we think about indoor air quality? Should we strive for the best, the most excellent quality, or should it just be good enough? Should it be acceptable? And what would make indoor air quality acceptable? I really like this definition, which is given in ASHRAE Standard 62.2, which describes acceptable indoor air quality as air in which there are no known contaminants at harmful concentrations, as determined by cognizant authorities, and which a substantial majority, 80% or more, of people exposed do not express dissatisfaction. So here then, air quality is a binary, it is not a categorical variable. So it is a series of criteria that enable us to define that acceptability, and it is those criteria that may change over time rather than the category of acceptability. So we shouldn't be striving for good air quality because I don't know what that means. It is the criteria that make up acceptability. So criteria that we have today may not be acceptable tomorrow, and therefore a building that was previously had acceptable indoor air quality may not have it tomorrow as new evidence emerges. So the key part of this definition is the harm that is caused, because we need to know the contaminants and the harmful concentrations. So we need to know which contaminants are present and the amount of that contaminant is present, and then we need to have an understanding of the relationship between the dose received by a person and the harm that that may cause. So contaminants are emitted in all spaces. They will disperse around and they will be diluted by the indoor air, and so they will form a concentration of the contaminant in that air. They are removed also by a range of mechanical factors generally. There are others too. So for example, biological contaminants may denature, but after time, given enough time and steady conditions, will reach a steady state concentration of that contaminant. Now during that time, that a person is in there, they're exposed to the contaminant, and then they will inhale some of that contaminant. So I'm only talking about a relationship with air quality through inhalation. I'm not talking about it through the skin or any other part of the body. If we breathe enough, we will inhale a dose. Not all of the contaminant that goes into us, into our lungs, stays in there, but that dose then will lead to a response. And if that response occurs over a period of less than 24 hours, it is generally known as an acute response. And for periods of over 24 hours, generally decades, it's known as a chronic response. And for the purposes of this talk, I am only interested in chronic harm. So we may start off life, hopefully living healthily, and as we're exposed to a contaminant or a range of contaminants, we may start to realize symptoms and acquire diseases and or disability, and it may even lead to our premature death. Now, there are a whole range of contaminants used in standards at the moment, and I invite you to go to the AIVC website at www.aivc.org and have a look at the extensive literature that is there. And one of the documents you might like to look at is Ventilation Information Paper number 36, which reports on an AIVC seminar that was held in 2017 in Brussels, which considered metrics of health risks from indoor air. What we found at that seminar was that it was not clear how a change to many of the metrics, say by 10%, would affect the occupant health and their comfort. And that generally that it was much easier to deal with acute risks rather than chronic risks. You can make some immediate change. The acute risks are easily observable, but for chronic outcomes, they're not. So we decided that we needed an indication of the relationship between dose and health consequences. But given different regulatory bodies specify different limits at the moment for different contaminants, we wondered whether shouldn't all thresholds cause the same magnitude of harm for different contaminants? We're also well aware that there was no such thing as a zero risk. And so if we accept that there will always be some risk from exposure to indoor air contaminants, can that risk be acceptable? Then how do we account for harm at a population scale and determine appropriate solutions, ignoring outliers? Therefore, can we determine contaminants of concern that have a direct effect on health and are commonly found in indoor air? At the moment, we tend to use these threshold values, which are maximum averages of airborne concentrations of hazardous material to which a healthy person can be exposed over some period of time, and it's often over a 12-month period, a year. And the WHO has threshold values for these three contaminants: particulate matter with a diameter of 2.5 micrometers or less, nitrogen dioxide, and ozone. And they are 5 micrograms per cubic meter, 10 and 60 micrograms per cubic meter, respectively. I'll come back to these later in the talk. Now, one way of assessing harm is to use health-adjusted life years, and there are two key metrics currently in use today. The first is the quality adjusted life year, which is used in the UK and Thailand and the Netherlands and a few other countries, which considers the life years lived in full health and then the life years lived with a disability. Whereas the disability adjusted life year, used by many other countries and the World Health Organization, considers the point at which a disease starts and then the life years lost due to premature death. A DALY then can be considered the sum of the years of life lived with a disability plus the years of life lost, and they are considered at population scale. The information is acquired using toxicological or epidemiological data, and we can account for the ages at which years of life lived with disability or years of life lost earlier occurs, so we can weight by age as well. The smart thing about DALYs is that they're cumulative for different diseases that occur from exposure to a contaminant. So for a range of different diseases, you can add them up, and then they are you could calculate the total harm from indoor air contaminants if you had a DALY value for each contaminant. So what might be present acceptable harm for other daily risks in life? Well, alcoholism around the world accounts for 1,200 disability adjusted life years per 10 to the 5 people per year. Smoking for 2,600 and transport injuries for 1,000. Notice that these DALYs are normalised by a population of 10 to the 5 people. There is previous form here. The Lawrence Berkeley National Laboratory in around 2012 published this work, actually 2011, in Environmental Health Perspectives, and it shows the disability adjusted life years lost per 100,000 persons on a y-axis. Now the y-axis here is log scaled, so every horizontal line up is 10 times more harm than the line below. And on the x-axis then we have a range of contaminants. Now they acquired this information by reviewing 77 studies reporting on indoor air contaminants concentrations in the US and other countries with similar lifestyles, such as the UK. They considered 267 chemical air contaminants in total. They calculated the annual health impact of contaminants, considering the total intake in houses in addition to the intake in other environments. So this plot is specifically for houses. The take-homes then are that PM 2.5 matters by more than an order of magnitude over the next contaminant, which is secondhand tobacco smoke. If we then consider secondhand tobacco smoke and radon, which numbers 2 and 3, they can be removed via source control. We can ask people to smoke outside. There are a range of radon prevention measures, but particulate matter is important because it's often very difficult to practice source control because emission sources come from things like cooking, combustion, hoovering, and it is pretty unreasonable, one may argue, to ask people to cook outside. Anyway, what it does do is allow us to see if I can get a laser pointer. It enables us to identify those contaminants that are probably the most harmful and therefore should be targeted for removal first, whereas all the others, unless evidence changes, can probably be considered less harmful and can targeted for removal later. So the rest of this talk then focuses on chronic harm in houses. And the aim of our work is fourfold. It was to build on the work of Jenny Logue at Lawrence Berkeley National Laboratory and identify the most harmful contaminants so that they can be prioritized for removal. Now, to do this, we had to do 4 things. We had to use existing epidemiological and toxicological data to determine a new metric called the harm intensity that relates harm to the mass a person is exposed to. We had to determine uncertainty in contaminant concentrations in dwellings. And we had to combine then the harm intensities and the contaminants to determine the total harm for each contaminant. We then ranked the contaminants by the harm that they cause. So let's start then by looking at contaminants. So here we have a range of contaminants. We built on the contaminants that LBNL started with. We removed a few because they were considered over acute periods and added a few more on after some consultation with the US EPA. On the y-axis, it is again logarithmic. The concentrations are given in micrograms per meter cubed, except for radon, which is becquerels per cubic meter, or mold, which is colony forming units per cubic meter. We looked at 136 studies. We considered 827 data sets, and this represents concentrations in houses in the global north. So we were not particularly interested in houses that might be considered niche, and so we did not consider indoor air quality in, for example, passive houses. We also were not interested in houses built, for example, of adobe and where cooking was conducted over open fires in a kitchen or living room. So what does this data set tell us? Well, it tells us that the most abundant contaminant is ethanol. So the most abundant by mass is ethanol, followed by PM10, formaldehyde, PM2.5, and nitrogen dioxide. Now, interestingly, the most reported contaminant by studies, the top three are PM2.5, formaldehyde, and toluene. If we use a tree forest plot, you can clearly see here how much the first four contaminants dominate by mass all the other contaminants found in the space. So next we had to consider a harm model. Now, I'm not going to go through this model in great detail because that's not the topic of the talk, and this model can be found in a related peer-reviewed paper. But to quantify harm, we followed two approaches, one based on epidemiological research and the other based on toxicological research. So here we have an epi-harm model and a tox harm model, and where data existed for both approaches for a single contaminant, we were able to pull that information together. The dose-response relationship generally follows a 1 minus e to the minus n relationship. But for the contaminant concentrations found in homes, we're operating at the linear part of that relationship, which means that we can create a new metric known as the harm intensity, which has units of disability adjusted life years per unit concentration per person per year. Now, you can replace the mass with becquerels or colony forming units where appropriate. We multiply that then by a representative contaminant concentration, and that will then give us the harm. There's something gone very wrong with this plot, but never mind. On the y-axis here, we can see that there is units of harm intensity and disability adjusted life years per microgram per meter cube per 10 to the 5 people per year. And just going to see if I can pull that down so we can see it a bit better. There we are. And on the x-axis is the same list of contaminants that we saw in the previous slide. What are the take-homes from this? Well, the take-homes here are that PM10 is the most harmful contaminant per unit mass inhaled per year. PM10 is second, chromium third, nitrogen dioxide fourth, formaldehyde fifth, and then the coarse fraction is also considered. The reason we consider the coarse fraction here is because the harm from PM2.5 is contained within PM10. So when considering total harm, we want to isolate the coarse fraction from the PM10. So then, if we consider the total harm, which is the product of the concentrations and the harm intensities, we can see that PM10 comes out as the most harmful. But remember that contained in that PM10 is the harm from PM2.5. So we also consider the coarse fraction. So PM2.5 remains the most harmful contaminant by around an order of magnitude, with the coarse fraction second, formaldehyde fifth, nitrogen dioxide fourth, and then later on come radon and ozone. Now, this suggests then that we should probably be interested in these contaminants here most, and that we should initiate measures to minimize exposure to these contaminants first before we consider these contaminants here. So if we wanted to limit the number of contaminants in a regulation or a standard, then we would only consider these here. Now, so the y-axis is in log form, but just to give you an example of just how big the difference is between these contaminants and these, I'll put it on a linear form here. And you can see then clearly that PM2.5 is much more harmful than the next most harmful contaminants, which probably go to radon or ozone, and then really that these contaminants here are less harmful by quite a lot. The tree forest plot reinforces this, and it really does show us that 6 contaminants account for around 99.5% of all the harm. An interesting take home from this is that the TVOC metric really doesn't matter here. If we want to focus on one volatile, we should focus on formaldehyde, and we really shouldn't worry about all the rest. Now that we have the total harm for each of the contaminants, we can now add them all up, and it tells us the total median harm estimated from exposure to indoor air contaminants is 2,200 DALYs per 10 to the 5 people per year. We can then compare them against the other daily risks that we looked at earlier in the talk, and you can see that it's comparable with, it's slightly less harmful than tobacco smoking. So this work then tells us that we can start to indicate contaminants of concern. So here we have 6 of them, and we're interested in PM2.5, the coarse fraction, nitrogen dioxide, formaldehyde, radon, and ozone. And the harm is given in the second column, and the harm intensity of each contaminant is given in the third column. And what's interesting then here is that the harm intensities tell us that the coarse fraction is about half as harmful per unit mass, and it's about 16, nitrogen dioxide is about 16 times less harmful than PM2.5 per unit mass. And if we go all the way down to radon, it's 136 times less harmful per unit of concentration. Now, if we were to put this in a guidance document, we might want to give the harm intensities so people can calculate harm in their own environments and for their own buildings, because clearly we would expect the concentrations to change for subpopulations of houses in the global north. Furthermore, these harm intensities don't just apply to houses, they apply to any building. In fact, they apply to any location where you're exposed to any of these contaminants for a long period of time. Therefore, we would also want to give limiting concentrations, the point at which the dose-response relationship ceases to be approximately linear. So these are given now in the third column. So the limiting concentration for the linear relationship for PM2.5 occurs above 50 micrograms per cubic meters, which is significantly below those found in many cities, but according to our analysis is well above the concentrations found in most homes and buildings. So now we return to the harm from WHO thresholds. Now these are often decided upon arbitrarily, and as I'll show you now, they're certainly not decided upon by considering the harm from exposure to these contaminants over a 12-month period. So if we hold the PM2.5 harm steady, this would give us 300 DALYs per 10 to the 5 people per year. And if we consider the same harm for nitrogen dioxide and ozone, we could allow the concentrations to rise to 53 and 231 micrograms per cubic meters per year. However, there's a problem with this approach. This increases the harm that people would be exposed to, or we would expect to occur in a population. It's also very inflexible. We know that these 3 contaminants are important, although this doesn't consider all contaminants of concern. But what if PM2.5 concentrations could be offset by low concentrations of the other contaminants of concern? Well, this sort of approach could be done using a harm budget, which sets an acceptable limit of population harm and then permits any combination of exposures so long as the harm stays below the acceptable limit. So for acceptable indoor air quality, the exposure would be to any combination of contaminants of concern, so long as they stay below some limit. It is used by the World Health Organization, who define a tolerable disease burden of 1 DALY per million people per year for drinking water. Now, this is considerably lower than the 2,200 DALYs per 10 to the 5 people per year that we have identified in houses. A good question to ask here is, would it ever be possible to lower the harm budget for indoor air quality to that required for water? I would suggest probably not. Would we even want to do that? How could we go about setting a limit? One way of doing this is to use a reference scenario. And as a demonstration of the principle, we've used a sample of homes. This sample was obtained by Brett Singer at LBNL in around 2020. He looked at 20 homes where the indoor air quality in those homes, and they were in California, complied with the code required for ventilation and air quality. So they all complied with the California Energy Code. And they found that PM2.5 had a concentration of 5 micrograms per cubic meters, formaldehyde 23, and nitrogen dioxide 9 micrograms per cubic meters. So the cause fraction was not considered here because there was no guideline value, and we expect the magnitude to change over time of these houses, for example, as in a reference scenario as more houses are tested and are compared to existing harms. So what we did is we took the concentrations measured in these houses. For contaminants of concern where we didn't have where they weren't measured, we took guideline values. So we took 100 becquerels per cubic meter for radon and 40 micrograms per cubic meter for ozone. And we added up the total harm for these contaminants, and it came to a total harm of 610 DALYs per 10 to the 5 people per year. So just to be clear then, by complying with the California Energy Code and thus ASHRAE Standard 62.2, the total harm for these houses on average was 610 DALYs per 10 to the 5 people per year. Let's now compare them against our other harms. So we have our 2,200 for dwellings in global, 1,200 for alcoholism, 2,600 for smoking, and 1,000 for transport injuries. And the question now then is, what next? Well, we're considering ways of standardizing harm intensities where it's considered in relative terms using a dimensionless magnitude. But we're also interested in your thoughts on this and what you think the barriers are to integrating harm within standards and guidelines and moving beyond threshold limit values. There's a few people that really need to be acknowledged. The people on the left contributed to this work, particularly Gioberti Morantes Quintana. But the work was funded by the University of Nottingham and the Chartered Institution of Building Services Engineers. We're also very grateful for all participants of Annex 86 who've been critiquing this work for the past couple of years, and for the Air Infiltration and Ventilation Centre who have promoted this work on our behalf too. So we look forward to discussing this with you in the future, but until then, thank you very much for your attention. I'll leave you with these summary points.